Okay, our second section of our Weather 1 unit is all about air pressure. We are reading pages 10 through 14. The air is cool and clear, just perfect for an overnight hiking trip. You've stuffed your backpack with your tent, sleeping bag, stove, and food. When you hoist your pack onto your back, its weight presses into your shoulders. That pack sure is heavy. By the end of the day, you'll be glad to take it off and get rid of all that weight. But here's a surprise. Even when you take off your pack, your shoulders will still have pressure on them. The weight of the atmosphere is constantly pressing on your body. Properties of air. It may seem to you that air has no mass, but in fact, air consists of atoms and molecules, which have mass. So air must have mass. Because air has mass, it also has other properties, including density and pressure. The amount of mass in a given volume of air is its density. You can calculate the density of a substance by dividing its mass by its volume. Density equals mass divided by volume. If there are more molecules in a given volume, the density is greater. If there are fewer molecules, the density is less. Pressure. The force pushing on an area or surface is known as pressure. The weight of the atmosphere exerts forces on surfaces. Air pressure is the result of the weight of a column of air pushing down on an area. A column of air extends upward through the entire atmosphere, as shown in Figure 4. The atmosphere is heavy. The weight of the column of air above your desk is about the same as the weight on a large school bus. So why doesn't air pressure crush your desk? Down, up, oh. The reason is that molecules and air pressure push all directions, down, up, and sideways. The air pushing down on the top of your desk is balanced by the air pushing up on the bottom of your desk. Air pressure can change from day to day. A denser substance has more mass per unit volume than a less dense one. So denser air exerts more pressure than less dense air. Measuring air pressure. A barometer is an instrument that is used to measure air pressure. Two common kinds of barometers are mercury barometers and aneroid barometers. Mercury barometers. Figure 5 shows the way a mercury barometer works. A mercury barometer consists of a glass tube open at the bottom end and particularly filled with mercury. The space in the tube above the mercury is almost a vacuum. It contains very little air. The open end of the tube rests in a dish of mercury. The air pressure pressing down on the surface of the mercury in the dish is equal to the pressure exerted by the weight of the column of mercury in the tube. When the air pressure increases, it presses down more on the surface of the mercury. Greater air forces the column of mercury higher. At sea level, the mercury column is about 76 centimeters high on average. Aneroid barometers. If you have a barometer at home, it is probably an aneroid barometer. The word aneroid means without liquid. An aneroid barometer has an airtight metal chamber as shown in Figure 6. The metal chamber is sensitive to changes in air pressure. When air pressure increases, the thin walls of the chamber are pushed in. When the pressure drops, the walls bulge out. The chamber is connected to a dial by a series of springs and levers. As the shape of the chamber changes, the needle on the dial moves. Units of air pressure. Weather reports use several different units of air pressure. Most weather reports for the general public use inches of mercury. For example, if the column of mercury in a mercury barometer is 30 inches high, the air pressure is 30 inches of mercury, or just 30 inches. The National Weather Service maps indicate air pressure in millibars. 1 inch of mercury is approximately 33.8 millibars. So, 30 inches of mercury is approximately equal to 1,016 millibars. Altitude and the properties of air. At the top of a mountain, air pressure is less than the air pressure at sea level. Altitude or elevation is the decrease or is the distance above sea level, the average level of a surface of the oceans. Air pressure decreases as altitude increases. As air pressure decreases, so does density. Altitude affects air pressure. Imagine a stack of books. Which book has more weight on it? The second book from the top or the book at the bottom? The second book from the top has only the weight of one book on top of it. The book at the bottom has a stack of the stack has the weight of all of the books pressing on it. Air at sea level is the bottom book. Sea level air has the weight of the whole atmosphere pressing on it, so pressure is greater at sea level. Air near the top of the atmosphere is like the second book from the top. There, the air has less weight pressing on it and thus has lower air pressure. Altitude also affects density. As you go up through the atmosphere, the density of air decreases. This means the gas molecules that make up the atmosphere are further apart at higher altitudes than they are at sea level. If you were near the top of a tall mountain and tried to run, you would quickly get out of breath. Why? The air contains 21% oxygen, whether you are at sea level or at the top of a mountain. However, since the air is less dense at a high altitude, there are fewer oxygen molecules to breathe in each cubic meter of air than at sea level. So you would become short of breath quickly at high altitudes. Okay, that wraps up section 2 of Weather 1.